Good afternoon, sir. My name is Lu Yangke. My student ID is MAT2009418. Today, I'm going to have a presentation for the deformation and extension of Brownian motion. First, we see what is Brownian motion. The phenomenon of irregular motion of suspected particles hit by molecules is called Brownian motion. Brownian motion is liquid that appears to be connected, but is actually composed of many molecules when viewed under a high-powered microscope. The liquid molecules keep doing irregular motion and constantly hit the suspected particles at random. When the suspected particles are small enough, due to the impact of the liquid molecules from all directions is not balanced. At a certain moment, the particle in another direction by the impact of the superstrong, resulting in particles and other direction of moments, which cause the irregular motion is particles, that is Brownian motion. And Brownian motion as a stochastic process with continuous time parameters and continuous state space is one of the most basic and simple stochastic processes, and many other stochastic processes can often be regarded as its generalization or generalization in some sense. It is also one of the most well understood and colorful stochastic processes to date. Today, Brownian motion and its generalizations are widely used in many pure sciences, such as physics, economics, communication theory, biology, management science, and mathematical statistics, etc. At the same time, because of the close connection between Brownian motion and differential equations such as heat conduction equations, it has become an important channel of connection between probability and analysis. First, we see the definition of Brownian motion. Consider a simple symmetric random walk on a continuous line. Suppose that every delta t time a particle passes, it randomly moves to the right. Delta x is greater than 0 with probability p is equal to 1 over 2, and move to the left 1 delta x with probability q is equal to 1 over 2. And each movement is dependent of each other. If delta t represents the particle positions at time t, and delta t can go 0, delta x is equal to c square delta t. Then we know that x 0 c squared t is the definition of Brownian motion. Next part, the joint probability density of Brownian motion. Let the Brownian motion is 0 initial value standard Brownian motion. Let x0 is equal to 0, t0 is equal to 0. For all 0 is less than t1, t2 to tn. The joint probability density function is s1 to xn, t1 to xtn is an odd multiple of xi minus si minus 1 and ti minus ti minus 1. Among them, p is equal to. We can prove that if the Brownian motion increments are independent and follow normal distribution, then the incremental joint probability density is equal to the direct communicate multiplication of their probability density function. The Brownian motion is equal to the incremental summation of the transformed determinant of 1. Then the joint probability density function of the Brownian motion can be directly plotted. Give the initial condition B0 is equal to x0, and for any t is greater than 0. The probability that the position of Brownian motion at the time t0 minus t is higher or lower than the initial position. The probability also 1 over 2, which is the symmetric of Brownian motion. Next part, Martingale's property of Brownian motion. What is the Martingale's? Some special stochastic processes have unique properties, and Martingale's is one of the most important stochastic processes in asset pricing. After that, the Btn plus 1 minus Btn correlation term retains the expected symbol and calculates the corresponding expected value. The Btn correlation term is directly put outside the expected value to obtain the conclusion. Let it be Brownian motion. Then it's for about Brownian motion is all the Martingales. Next part, the first entrance time or first passager's time. First, we see what is the first entrance time or first passage time. First entrance time or first passage time is a classic of random moments. It is the moment when a random process first arrives at a set of state. Let it be 0 initial value standard Brownian motion. Then TA represents the time of arrival at A for the first time. The maximum. And represent the maximum Brownian motion on 0 to t. When A is greater than 0, there is the following event equivalence relation. That is, if the time to arrive at A is less than or equal to t, the maximum reached by Brownian motion on 0 to t must be greater than or equal to A. Hence, the probability of both is equal. According to the full probability formula, it is obvious that P is equal to 0. It is also known from the symmetry of Brownian motion under the condition of TA is less or equal than T. That is, when the Brownian is equal to A, these two are equally possible. That is, the possibility of both is equal to 1 over 2. That is, one of it is 2. So when A is greater than 0, we know that 2. So they also have 1 minus 8. Then the empty distribution function is this. It is known that FA is continuous and its derivative axis and its continuous expect for A is equal to 0. Therefore, MT is a continuous random variable and its probability density function is Pa is equal to 2 over the square 2 pi t, etc. When A is less than 0, there is P. By the symmetry of Brownian motion, so far general A in R, there is next part, the deformation and extension of Brownian motion. First, the Brownian motion observed at some point. Brownian motion observed at some point assume that for t Sn is equal to the Brownian t and x. Among them, tx is equal to the minimum of. It means that once the random process reaches x for the first time, it is observed and stay as x, which is called Brownian motion observed at x, and it is mixed random variable. Its distribution function is for y if y is greater than x, equal than x, and less than x. Among them, you can see the probability is the Brownian motion observed at some point. Next, we study the Brownian motion reflected at a region. It is called Brownian motion reflect at a region when y is less than 0. The possibility is equal to 0. When y is greater and equal than 0, then is equal to. Next part, we study the geometric Brownian motion. Geometric Brownian motion, also called exponential Brownian motion, is a stochastic process in continuous time, in which the logarithm of a random variable follows Brownian motion. Geometry Brownian motion has applications in financial mathematics and is used to model stock price in the Black-Scholes model. Can use in the financial mathematics. Black-Scholes model is widely used. It is a geometry Brownian motion and can be directly obtained from Brownian moment generating function e to the power of t over 2 and 2t minus e to the power t of t. Next part, we study the integral of Brownian motion. Let st is equal to the integral of the Brownian motion, then it is the integral of Brownian motion. We can prove that d bt is equal to dt plus dt dbt equal to t. It is equal to 0. Therefore, by integrating from 0 to t, we have which is equal to so it is so it's the integral of Brownian motion. That's all. Thank you for your listening.